Thank you for the invitation to speak in this learning seminar. Um, as the title of the talk suggests, I want to talk about some Diophantine aspects of the character varieties, which have been discussed in the past few lectures in the seminar by Professor Goldman. And coming from the Diophantine point of view, I want to maybe begin by providing some general motivation for the main theorem that I want to discuss today. I should mention just before I dive in that this being, I believe, sort of a learning seminar, I try to keep the style somewhat informal, and in some places it'll be informal by necessity because it's partly relies on some work that is currently being written up. But I hope that is okay. So some general motivation to discuss is the following. I want to we can begin by considering, suppose we have some system of Diophantine equations given by polynomials G1 through GL in M variables with integer coefficients, and let's call the system V. And on this, on top of the system, we can consider sort of a parameterized family of Diophantine equations, let's say F1 up to Fn equal to some values of integers Kn. So we can obviously view this parameterized family of Diophantine equations as a morphism from this fixed variety or scheme V to affine n space, where n is a number of these parameters that I'm varying. And we can denote by V of k the fibers of this morphism. And of course, given a general system like this, there are some very basic questions one can entertain, one of which is whether or not, if we look at the image under this F of all the integer points on V, this viewed as a subset of Z to the N is decidable in the sense that there's a procedure to decide, given any point inside Z to the N, whether or not it belongs to this image. In other words, whether or not the set of integer points on this fiber VK is non-empty. And maybe somewhat related to this or somewhat separate from this, we can ask for each K whether there is some structure, interesting structure on the integer points, whether there's a finite set of integer points or whether the integer points are finally generated in a suitable sense or some other structure. And one can also ask, if one has a satisfactory answer to both 1 and 2, then whether there is some pattern to the behavior of the assignment K mapping to the set of integer points as K varies. And just one thing to note is that, of course, already in question 1, there are examples of such Diophantine equations where you do get undecidability of the existence of integer points on these fibers. So it is of interest to some of us to find interesting examples of Diophantine equations or families of Diophantine equations for which the first question has an affirmative answer. And there are numerous examples where one can have a affirmative answer, and I just give only a few of them. But just to point out, here in these examples, the ambient variety V is going to be just the affine space. And of course, if I have a linear map defined over Z, then we can find out all there is to know about the integer points on the fibers. And similarly, there's extensive theory for level sets of quadratic forms. And of course, by Baker's work for higher degree forms in two variables, for example, by examples of two equations, one has an effective theory. And the fourth example that I want to mention, and I want to maybe emphasize for later use, is the example of linear representations of reductive algebraic groups. So if I have some reductive algebraic group G defined over the rational numbers, and I have a rational linear representation of G on some affine M space, and I suppose I take the finitely many generators, F1 through Fn of the ring of invariants of G acting on affine M space. There's a finite set by Hilbert. Then once I fix all the invariants, and if I can ensure some minor condition, namely that, so if I denote by fixing the invariants these VKs, if this VK is a closed orbit under the action of the complex points of the reductive group G, then Borel and Harisandra showed that the set of integer orbits on VK under the action of the integer points of G is finite. And moreover, there are results, for instance, by Grunewald and Siegel, going to show to a degree these all of this theory can be made effective so as to get a affirmative answer to the first question, for example, in the previous slide. And so this is all quite satisfactory for the class of varieties that are sort of homogeneous spaces for linear group actions under for reductive algebraic groups. And one possible goal is to go beyond this, beyond the examples, by looking at examples of varieties which have sort of inherently non-linear symmetry, or are or have partial linear symmetry. And so this brings us to the character of varieties that I want to focus on for the remainder of this talk. And just to set up some notation, I'll write throughout this talk. I'm only going to focus on character varieties where the structure group or the coefficient group is SO2. So I'll usually suppress this from notation. And so given any connected, let's say, compact manifold M, we can denote by X of M the so-called SO2 character variety of M, which is the geometric invariant theory quotient by simultaneous conjugation action of SO2 on the space of homomorphisms from the fundamental group of M to SO2. So again, maybe I should assume compact or at least finally generated fundamental group. And given such XM, this has a natural model over the integers such that the integer points correspond precisely to those representations with values in the complex points, such that the trace of the row under for any alpha in the fundamental group is integer. And given such integral structure, one can see that the natural action of the outer automorphism group of the fundamental group of the manifold acting on Xm preserves the integer points. And maybe one additional notation I'll introduce for convenience's sake later on is if I have a finite union, finite disjoint union of connected compact manifolds, then I'll just define the character variety of the union to be the product of the character varieties. And so there are these examples which I think were already mentioned in Professor Goldman's earlier lecture, so I'll briefly go over them. So if M is just a circle, then one can identify X of M with the affine line by means of the trace of a local system along the sort of the generating loop along S1. And if M is a pair of pans, meaning a sphere with 3 holes, then one can identify the character variety with affine 3 space by recording the 3 traces along the boundary curves. And because the 1-hole torus drawn here and the 3-hole sphere, they have the same fundamental group, and clearly X of M only depends on the fundamental group of the said manifold. We see that X of M in this case can also be identified with A3, where these loops or simple closed curves we can take to be the ones drawn here. And of course, these two depend on this result of shown invoked, as Professor Goldman mentioned, about identifying the quotient of the product of SO2 squared modulo the conjugation action of SO2 with affine 3 space. So having introduced this general notation, I want to quickly turn to the class of character varieties of surfaces and state the main theorem, which will be the focus of this talk. So here in this talk, I'll denote by sigma a surface of type Gn with some numerical condition. So the surface has non-trivial moduli. And let's say I'll denote, for simplicity, I'll label the boundary curve as sigma by C1 through Cn. And I'll denote by gamma the pure mapping class group of the surface, which is the group of isotopic classes of the orientation preserving diffeomorphisms of the surface that fix the boundary pointwise. This maps into the outer automorphism group of pi1 by precomposition, and so this gamma acts on this character variety X of sigma, and moreover, by the construction of gamma, we see that this preserves the morphism from X to affine n space that takes a representation of a local system and prints out its traces along the boundary curves. So this gamma preserves the fibers of this morphism. And so the main theorem that I want to discuss concerns the integer points on the fibers denoted xk here. So the first statement is that this morphism sends the integer points on X into a decidable subset, meaning that for each n tuple of integers k, there is a way to decide whether or not xk admits a integer point. And more strongly, it turns out that for each k, xk of z is effectively finally generated in a precise sense, which I sort of state here, but maybe not precisely enough. But hopefully it'll become clear later on as I discuss the proof. So there is a finite set of morphisms that can be effectively determined from some algebraic groups Gi into Xk, such that each Gi admits an effectively finally generated lattice of integer points, and such that the integer points on xk are generated. Apologize for lots of typos. Are generated.
May I ask?
Oh, yes.
I mean, do you assume that the boundary is not trivial, or it's include also the case that boundary is trivial?
This includes also the case where the boundary is trivial. So in this case,
what the traces you are looking at, what are to check the integrality? What's exactly now the definition? Integral. Sorry, integral is for all the elements, even though we know that finitely many are sufficient. Okay, understand now.
mm-hmm.
Okay, yeah. Sorry, it's my fault. Yeah, I thought that you assumed.
No. Thank you. Right. Yes. So right.
Your definition. It's known that it's enough to check the integrality on finitely many, but your definition does not really. Okay, I'm sorry. That's fine. The definition is for them. It doesn't matter. Okay.
Yes, right. I do not make it clear in the definition of integer points, but it is true, as Professor Lubowski points out, that to check that a point in here is integral, it suffices to check there is a finite collection of loops against which you have to check integrality to deduce the integrality in general. So by this, for example, one can use Porchesi, result of Porchesi, or maybe Magnus, I'm not sure in this case, saying that the traces along the elements, the trace functions along the elements sort of finally generate the coordinate ring, so the sense of the character variety. So, okay, but so just to elaborate on this result, so we have these finitely many effectively determined morphisms from some algebraic groups into xk, where each gi has integer points that are sort of effectively finally generated. And moreover, the images of these integer points, together with the mapping class group, will cover the entirety of integer points on xk of z. So that is what is roughly meant by effectively finally generated. Are there any questions about the statements?
So a particularly interesting case is where R is 0, or just finitely many points, and you don't need B, right? In other words, that the integer points of xk in many situations will consist of finitely many gamma orbits.
So, right, as we'll see in the one example, the Markov example, which I'll turn to, that is true.
I understand it's not true in general, but so you have to fatten it up by these algebraic groups. Yeah, you'll explain.
Yes, yes, it is somewhat necessary in the general case, but nevertheless, counting these arithmetic groups, one does get sort of finite generation in this precise sense. So I should mention first turn to the classical case of the Markov cubic. Sorry, before actually turning the page, I want to mention, so because I recognize some people in the audience, so this result by itself is not 100% new. There are at least parts of this result, or sort of a result going partway to this that was obtained earlier, and which I'll comment exactly what was obtained earlier, and so some of the talk for some people in the audience might not exactly be new, but hopefully there are some newer aspects that I'll point to as well. But just in case there are any new members in the audience, I wanted to go over the proof of the older result as well. But so turning to one of the simplest examples, the case of the one-hole torus, GNN equal to 1, 1, then we already mentioned the character variety of the one-hot horse can be identified with the affine 3 space. In this case, the boundary trace is just going to consist of fixing the trace of one curve, the boundary curve here. And so it's going to be a map to the affine line given by some polynomial function of the generators, these elements. It turns out to have some very nice symmetric looking formula. And so each of the xk's, the fiber of this boundary trace map, is going to be an affine algebraic surface given by this equation. And one can recognize that the mapping class group on xk is essentially generated by, well, these are generated essentially by the Dane twists along the curves underlying each of the loops A and B that generate the fundamental group of the surface. And one can show by computation that the effect of each of these Dane twists is such that xyz is mapped to x comma z comma xz minus y and so on. So obviously this is a nonlinear map. And this is what I alluded to when I talked about wanting to look at varieties with nonlinear symmetry. And in this particular case, it happens that one can sort of extend the gamma action a little bit by a larger group of finite index with that are generated by permutation of the coordinates. Obviously, by the symmetry of this polynomial, there is this action of S3. And also, one can consider the so-called Vieta involution, which is obtained by taking x, y, and z here and looking at this equation viewed as, let's say, a quadratic equation in the third variable z and mapping it to the conjugate root xy minus z. So this is the polynomial map. And the classical results that can be traced back to a work of Markov. And so I attribute it to Markov, even though it wasn't explicitly stated this way. An interesting result is that as long as k is not equal to 2, one can show that the set of integer orbits under this action of the mapping class group is finite. And the idea, just to state it roughly, is that by playing around with these actions, one can assume that given an xyz, one can put it into a form where we can assume this kind of inequality holds. Otherwise, we can always bring xyz to a smaller set. And then one can play this inequality against the fact that z times xy minus z in absolute value is equal to this quantity, where each of these terms must be larger than x and y. And so one plays these two inequalities or against each other to create some tension, and so as to get that the smallest coordinate must be bounded above in absolute value in terms of k. And then once you fix your value of k, we can see that this equation gives us a nice conic equation on which, for example, this tau of a gives you a sort of a rotation on the hyperbola or the conic. And so one can believe that this tau of a will act on this conic co-compactly, except for some degenerate cases. And so, so this will suffice us to bring the integer points into a compact set so as to get the finiteness. But that's the general idea. Of course, one should point out that this kind of use of the explicit equation will not be very feasible for general character varieties of surfaces. But before turning to the proof, I want to maybe mention three things. One is, I thought it was sort of elementary enough that it will be worth mentioning. It's a corollary of the main theorem, or rather the proof of the main theorem, which is that if I fix some g greater or equal to 1, although it's only really new when G is greater or equal to 2, then we have a procedure now to determine whether a given element A inside SO2Z is a product of G commutators in SO2Z. So, well, this is an elementary Diophantine problem which we're now able to solve as a corollary of the theorem. Another result, another thing that I want to mention is about the earlier work that sort of precedes this main theorem of today. It turns out that in general, the set of integer points on xk need not decompose into finitely many mapping class group orbits. And so one can recover some sort of a generalized finite generation in terms of the so-called finitely many non-degenerate integer points and some Zariski closed subsets. Here, more precisely, I define the degenerate locus of xk to be the union of images of non-constant morphisms from the affine line to xk. It turns out that this is in the orbit of a proper Zariski closed subset of xk, and on the complement, the set of integer points decomposes into finitely many orbits. And in fact, one can give a moduli theoretic interpretation of the so-called degenerate locus, but I won't delve into it. And I want to, in the spirit of sharing sort of older results, and in the spirit of this talk about decidable Diophantine equations, I thought it would be worth mentioning also that in the case of the Markov surfaces, the Markov cubic earlier, it turns out, so if I have an affine algebraic surface like this, then in fact, any Diophantine equation on this algebraic variety is sort of, the integer solutions can be effectively determined. So this provides a class of varieties with Zariski dense set of integer points, of course, of dimension bigger than 1, for which one has a sort of a complete theory of Diophantine equations, at least over the integers. So I thought that was worth mentioning. And of course, the ultimate hope would be that maybe not just for the Markov case, but for the general SO2 character variety of surfaces, a similar sort of a complete effective Diophantine analysis of integer points on subvarieties can be established, but that we don't have. So I want to turn now to the proof of the main theorem. Before I begin, are there any questions about the earlier slides?
In the Markov case, what was the algebraic group that was that the orthogonal group?
You mean these GIs that I mentioned? Right. So in fact, what these GIs will be is, so I will be mentioning this. In fact, I think I do mention it on the slide that I was mentioning here. So it turns out that these groups will be precisely, well, not precisely, but these will be in, typically these will be sort of products of centralizers of monodromy along some collection of curves. So maybe if I go through this slide in detail, it'll become clear what I mean. But right, so in fact, so G will be a product of subgroups of SO2. And in the case of the Markov surface, typically I should say the GI will just be just GM. But in the case when K is equal to 2, the case excluded by Markov, you need to consider other G like SO2Z, basically. And for general surfaces, the situation is more complicated, but they can be effectively determined. So the general picture, or at least a motivating picture behind the proof, is the following construction, which is that if I have a past decomposition of the surface, by which I mean a collection, a maximal collection of pairwise disjoint non-isotopic essential simple closed curves on the surface. When I say essential, I mean they are not contractible and they do not sort of talk to the boundary. So for example, in the case of a genus 2 surface with one hole, what I've drawn here is an example of a past decomposition, the union of these simple closed curves. Given a past decomposition like this, one has an associated morphism from xk down to affine space of half the dimension that takes a representation or a local system on sigma and records its traces along these curves. And it turns out that the fibers of this morphism are going to be generically, in a precise sense, algebraic tori or some finite quotients of algebraic tori. And there is a subgroup of the mapping class group that acts on xk preserving this morphism, namely the group generated by the Dane twists along these simple closed curves, which I neglected to explain. The Dane twists, I mean, I take the surface, I cut my surface up along one of these curves, I twist, I get two cylindrical ends, twist one of the ends 360 degrees, and then glue them back together and up to isotopy. This gives us a mapping class group element. And it's clear that such an operation will leave the traces invariant. And so if this gamma p generated by the Dane twists along these AIs provides a group that acts generically co-compactly on the fibers. And so the idea is that the reduction theory on xk of z under the action of the mapping class group should follow the following pattern. Oh, just before I move on, I should mention that this morphism also, there is an algebraic symplectic structure on xk due to work of Professor Goldman. And with respect to this, this morphism furnishes a maximal Poisson independent family of maps. So it furnishes a completely integrable system in the Hamiltonian sense. But that's, we don't, all we need is this structure map. And so the idea is that using the terminology of this integrable system, if I have a row inside xk, I want to first maybe find a past decomposition P such that the projection of this row under this map but lies inside some compact subset of the affine space that is determined a priori. So depends only on the initial condition of boundary traces. Okay, so that's the first step. And for this, one can employ sort of differential geometric tools. And the second step is the step that is sort of can be generically established by this picture, namely on each of the fibers of this projection. One can try to do reduction theory. In the generic case, the Dane twist will suffice, but there will be cases when the fibers are wilder than these sort of quotients of algebraic tori. And the upshot is that even in these cases, you can essentially view the fibers as affine homogeneous varieties for some group, which is, as mentioned before, a product of centralizers of monodromy along these these curves AIs. The reality is more complicated than that, but that's the motivating picture. And lastly, I felt that it would be worth sort of separating this third fact out, is that a priori we have these infinitely many pairs of pants. For each pair of pants, one has this reduction theory along the fibers, but there are infinitely many pairs of pants. But the nice thing is that up to mapping cluster of action, there are only finitely many pairs of pants, or up to isotopy. So I think this is something about the topology that's important is being used here. So I should say that the part A, which I'll next describe, was established earlier. So I'll try to go through this somewhat briskly. And part B is really where the newer part of my research comes in, and where the linear arithmetic group results of Borel and Harischandra and Grunwald and Siegel come into play. That's the reason I mentioned them. But
there's another reason to mention them, and that is that your theorem is exactly the analog, in slightly generalized, of the Borel-Harischandra theorem about reduction theory. You're doing reduction theory in character varieties, and
right.
And it's true that with B you're using the reduction theory in the linear case, but in A you're using some really new ideas. So don't go too quickly over that.
Okay. Yes. Thank you. Right. So so to turn to the proof of A, I believe I only have until 12:50. So I will try to sort of manage the time between parts A and B well. But in part A, essentially, part A, I want to label just as there was sort of a linear arithmetic finiteness in part B and topological finiteness in part C. There is sort of a geometric finiteness coming in for part A, which is the following. So namely, if what I want to do is I want to find, given a pair of given a representation or local system on sigma, I want to find a pair of pants decomposition such that the traces of that row along the curves of the pairs of pants are very small. That's what I want to achieve. And there's a way to encode the traces of the elements in SL2C in terms of the translation lengths of the given element as SL2C acts on the associated symmetric space, namely the hyperbolic 3 space. And so here, this is the infimum translation length of any element inside the hyperbolic 3 space under the action of that particular group element G. And one can define, given any local system like so, the systole of the local system to be the infimum translation length of a essential simple closed curve. Again, essential means non-contractible and non-peripheral for me. And we can do some simple induction on the topological type of sigma to show that to establish step A, it suffices to show that given the boundary conditions K, if I fix the boundary traces, then the systole function as defined above here is sort of uniformly bounded. And of course, one might recognize that this is somewhat similar in spirit to the result that, for example, if I have a hyperbolic surface of a, for simplicity, let's say I have a closed hyperbolic surface of genus G, then the systole on that is going to be uniformly bounded, independent of what hyperbolic metric that I choose. But of course, the maybe the complication is that here, unlike the case of hyperbolic structures, there's no sort of canonical associated geometric, like a metric on sigma associated to rho. But still, we can try to introduce some metric to say something about the behavior of the systole. And the basic idea is that once I fix a background metric on the surface, and I consider the hyperbolic 3-space bundle on sigma associated to that given fixed rho, and I construct this family of metrics given by a pullback along some section of this bundle of epsilon times the background metric plus the hyperbolic metric on H3, where this epsilon is some parameter that will let go to 0. Then by construction, the systole of rho defined to be this quantity above is going to be bounded above by the systole of the Riemannian surface sigma with this metric, Riemannian metric sigma epsilon. And by definition, the systole of a Riemannian surface is the infinite length of an essential closed geodesic on sigma, at least here I define. And by results of systolic geometry, one can show that this quantity for any Riemannian surface is bounded above in terms of the volume of the Riemannian surface and the boundary, the lengths of the boundary curves appropriately defined. And so I quote here sort of the names of some contributors to this kind of systolic inequality, not an exhaustive list. But now the upshot is that, of course, you can have an arbitrary section, and then these volumes and the lengths can be very, very large, so making this kind of bound useless. But the idea is that if I choose S to be a harmonic section with some boundary conditions, then one can show that as I remove the dependence on epsilon by letting it go to 0, one can show that these two terms become bounded respectively in terms of the Euler characteristic of the surface and K as epsilon go to 0. So this kind of technique was used by Reznikov in a proof of the so-called Milner-Wood inequality, and so there's some modification that goes in, but the core idea is the same there. And so, of course, one has to end by noting that there is an existence result for harmonic sections that make this possible by results of Donaldson, Hamilton, and Corlett. So combining these tools, one can see that by this uniform bound, one sees that the systole of any local system rho inside xk of c is uniformly bounded. So this establishes part A. I should mention that this bounds on the volume very much uses the fact that H3 is hyperbolic. So there are some subtleties that do not arise here, but rear their heads when you try to go beyond this rank 1 case. Now, in the remaining few minutes, I want to maybe give an impressionistic view of the part B, the reduction theory, the linearized reduction theory. Maybe, and I want to sort of stress what it is that sort of makes the sort of finite generation really possible. The idea is that, of course, generically we know that things are good and the mapping class group action suffices to, the data twist suffices to get a sort of finiteness by a co-compact action, but there are cases where things do go bad. And basically, I have this, if I have a Pan's decomposition, I'll denote by sigma of P the surface obtained by cutting up the surface along the Pan's decomposition. And I have this immersion of sigma P to sigma, which induces a map by functoriality from x of sigma to this to this X of sigma P, which is just a product of these, the character varieties of the components. And the idea is that, of course, the fibers of this F can be very bad. That's the idea. And this being very bad comes from essentially the fact that if I look at each of these X of sigma I, a point in here need not determine a SL2C conjugacy class of a representation uniquely. So there can be an infinite set of conjugacy classes. And so when we try to glue representations or local systems along these curves, we see a jump in the dimension of the varieties. That's one way to put it. But the idea is then, therefore, we want to work essentially, instead of the character variety side, the so-called representation variety side, or the Hom sets from pi1 to SL2C and so on, with the action of SO2C. But in general, this cannot really be achieved, except that in the case when you are looking at sort of local system with integral trace, one can sort of recognize that the image of such a representation, assuming irreducibility, for example, will be conjugate to a representation into some order of a quaternion algebra, which can be effectively determined by the data of the representation. And so the idea, I really try to draw a caricature here. The idea is that whereas in general, the lift from the character variety side here to sort of the representation variety side will introduce sort of infinitely many orbits. If one looks at integer points only, then there is a way to restrict to sort of finiteness of the fibers of these projection maps from pi of d. Very impressionistic statement, but the idea is that once that is done, there is a way to describe the gluing data on the representations side from the local systems on the three-hole spheres or the pairs of pants to gluing to the entire surface like this, which the finiteness in general can be established using these results of Brown and Harshchandra and Grunwald and Siegel to get effectivity. I should mention that there is some Hassan-Minkowski at play here to get this effective determination of the discriminant of the quaternion algebra. So there is there's some more to be said, and not all the details are described here. But I wanted to maybe give an impressionistic view in this learning seminar. And I think that's the end here for me. Thank you so much.
More questions?
Maybe oh, sorry, please go ahead.
Yeah, there's one point that I think is worth mentioning, is that all these finiteness and decisions are for Z only, or an imaginary quadratic ring of integers, and not a more general ring of integers. So if you increase the number field over which you're defining, the mapping class group doesn't get bigger. And these, it's just worth mentioning that this is really a theory of Z.
Right, yes, right. Right. Of course, there's a defect that comes from a defect. Like the mapping class group doesn't increase as I change the field. There are some questions that can be asked whether one can recover sort of finite generation by adding in these arithmetic groups. Yeah. But I feel that that's a little bit out of at least my reach at the moment.
But Peter, this you don't expect the integral point, the GLNZ to act with finitely many orbits on O to the n, right?
No. It's just like in Borel. I compare his theorem very much to Borel-Harischandra. It's a character variety version. So in Borel-Harischandra, if you change the ring, then the group gets bigger. And so everything is still finite. But here, the group is the mapping class group. And for some remarkable reason, it's working very well with integers and any discrete ring in the complex numbers. So an imaginary quadratic ring. And whether you can use this in the more general case is, I think, as Junho said, is really a basic question. So, to me, this is actually this differential geometric argument. If you look at the reduction theory, the key insight that Borel-Harischandra use is a Ziegel set. And that's what's being replaced here by the differential geometry. I mean, this is a nonlinear Borel-Harischandra theorem, in my view. Yeah. For Z only.
I should mention that maybe in hindsight, the differential geometry is not so, it sort of, I think, can be motivated as an analog of the Minkowski inequality in a sense. So it's not too far-fetched to think of it this way. But of course, as I mentioned, once again, there are some special properties of SO2 that I'm using here that do not easily generalize to higher rank groups, and so there are some difficulties.
I had a naive question. I thought that your definition of X sigma was precisely that quotient, that omma of pi 1 sigma SL of quotient by SL. So why there is that surjective? I thought that they were the same, but maybe I missed the definition of X sigma.
Sorry, you mean why is this surjective? Or
why the two are not the same? The same. Maybe I just missed the definition of X sigma. I thought that they were the same.
Sorry, so X sigma was just the character variety of sigma. So sigma is a surface here of genus G with n boundary curves. And so this is all the right, maybe here, the issue is the absence of this another check here. So if I take the GIT quotient, then it's the same by definition, but the GIT quotient sort of collapses a lot of orbits to a point. And so because of this, there is some complication that arises.
So what you are considering there, when you put just one bar in that case, you just take the orbits.
Sorry?
What do you mean? What do you mean with the quotient there? Because then, I mean, if I take just the space of the orbit, then the GIT quotient is collapsing together a lot of orbits, and that's the subject that you are taking.
Right. Yes.
Okay.
Yes.
Okay, great. And I had another question. So, does your work relates to the cell decomposition of Mellit for this character variety? Recently, Mellit has proved the curious unleashes for smooth character variety, and he proved it using a decomposition of the character varieties in terms of in some cell of the shape C to the n times C star to another power. I don't know if these cells are defined over the integer, but can this decomposition be used to compute a point over the integer of character varieties?
That's a good question. I don't have an answer to that. To be honest, I'm not quite familiar with this work that you described
But it seems to me that there are similar ideas. I mean, this idea of, there are decomposition in pair of pens and then a braid group acting. I don't know if there is any straightforward relation between the two. I mean, this fact of wanting to decompose the variety of the pair of pens.
I see. I'd certainly be interested to learn more in this.
Thank you. Thank you.
Thank you.
If no more questions, thank you very much once again.
Wait, may I make a comment?
What is the question? Oh, sorry.
Just a small, sorry, I was a little late. I just wanted to make a comment. Number one, it's a really cool result that you can write down the angle variables for this integrable system. And I'm sure you know that this whole story is related to the Hitchin integrable system through non-abelian Hodge correspondence. And we're just trying to, and over there, it's completely hopeless to write down the action angle variables for a generic curve, at least. I was, so in order to compare the two things together, does your integrable system have a section?
I mean, to be brief, because I think there's isn't there another seminar coming? But
we can talk later.
I'm not quite sure about the relation between the two, but so this so-called integrable system has non-compact fibers, whereas the Hitchin is by vibration is by abelian varieties. So it's a bit.
No. They're open sets in an abelian variety. You can compactify them. So the Higgs moduli space itself is non-compact. So his result is that the
vibration has, they're generically abelian varieties, right? The fibers?
Dense open sets in abelian varieties. You can complete them to abelian varieties.
No. The Hitchin vibration is proper. The moduli space of Higgs bundle is not compact, but it's fibering over an affine space, so there is no contradiction.
Or maybe you were thinking of the cotangent bundle that embeds into the Hitchin space.
Yeah.
And then
right. The Hitchin's original paper, right?